Hey everyone, Mr. Newman here. I wanted to go over this problem because this is calculator heavy, and that way you have this resource to pause and use the calculator as you can, and that way we're not waiting for everyone in class. And so my hope is whenever we do calculator heavy calculator heavy problems, I'll hopefully make a video notes on it. So Snoopy in his plane is 4,500 feet above the ground. He fires a projectile straight up at 340 feet per second at the Red Baron, who is maintaining a constant altitude of 5,200 feet. The position of the projectile is represented by the function, and here's the function we're going to use, where v sub 0 is the initial velocity, and s sub 0 is the initial position. So first thing, yes, this is the position of the projectile. Sorry, the typo there. But we need to fill in v0 and s0. Okay, and those are common notations that you'll see for initial velocity and initial position. So it told us that we should have to read carefully. This is the projectile is being launched from Snoopy, so he is 4,500 feet above the ground. So that's going to be s sub 0, 4,500, and the initial velocity he said here was 340. Now we want to think about, are these positive or negative? 340. He fired it up, so that's going to be in the positive direction. So it is going to be positive 340. So our position function is s of t equals negative 16t squared plus 340t plus 4,500. Oops. Now that we have that, to find the velocity, remember that's just the derivative of position. So let's take the derivative. We call it s prime or v of t. Derivative, so you bring the 2 down, multiply it, and then the plus 340, 4,500, of course, the derivative of that is 0. Then for acceleration, remember that's just the derivative of velocity. So acceleration, or v prime or s double prime, is going to be negative 32. So to find the average velocity, what we're going to want to use is plug this in. So we're going to find s, we'll do 5 first, minus s of 1. All divided by 5 minus 1. Now this is where it starts to be really helpful to have the calculator. So you can see what I did here. I went ahead and plugged this into y equals, okay, when you press, y equals there. What I have is I've got the function, and of course when you, let's go zoom fit, zoom standard. Sorry, reset that. Okay, when you have the function, you can graph it and you can quickly find the values using trace. That's the nicest way to do that in my opinion. Or you can also use a table. But notice I try to trace zoom here and I don't see the function. That's because it's way off the top of the screen. So I want to first of all think about, okay, where, if I zoom out, in fact I could even do zoom fit, that is zoom 0, of course, whoopsie. You can scroll down or you can just press 0, right? If I just press 0, enter a 0, then it jumps down there automatically. If I try to zoom fit, notice we don't have the entire projectile. So that's not good. We need to find out where is it going to hit. We actually already see it's going to hit there on the left around negative 9 or so. But on the right, where does it land? And I could use a guess and check, but I can also quickly find this because since this is a quadratic, I know the quadratic formula finds the zeros, right? So let's just do that. Now, if you don't have one of the fancier new calculators, you can't press alpha y equals. If you can press alpha y equals enter, I would strongly recommend making that fraction. Otherwise, you need to use parentheses and division symbols. So let's do this. Opposite b, plus or minus, we'll do plus first. The square root of b squared, normally I'd put that in parentheses, but I know it's positive, so we're good. Minus 4ac, whoopsie, gotta make sure I type this in correctly. 4ac, I use second delete to do insert there. 4ac, 4,500, all divided by 2a. Okay, enter. We get that negative 9. We already knew that was going to be the case. Let me come up here and click enter to bring that down here, and I'm going to go all the way to the left and plug in a negative there. So that's the plus and the minus. Aha! 30, just a little bit above 30, that's where it's going to land. So what I want to do is I want to go up to my window and I'm going to go down to x max, and I'm going to make that a little past 30, maybe just 31, right? The minimum, I don't care about any of the negatives, so I'm just going to delete that, make that 0. And now if I go to zoom fit, that's zoom 0, press 0, and it can start graphing it, and look, there it is. So remember, this is not a position versus position graph. This is a position time graph, right? So the x is not going up and to the right, this projectile. It's going straight up, but as we go to the right, that's time that's moving forward. So what were we looking for? Oh yeah, the average velocity. I like to click trace, and you can type in 1, enter. There we go, 4,824. 4,824. Probably should have done the other one first. Let's do trace 5, enter, 5,800. So 5,800 minus 4,824 divided by 5 minus 1. Again, I can use my handy dandy calculator for this. Let's type in, whoops, quit, not that, there we go. Again, you will need to use parentheses if you don't have a fancy dancy calculator. Probably should have used the old version, but, well, I want to show you guys how slick the newer one is. Anyway, all right, enter. 244 is the average velocity. 244. One thing to watch out for, remember, it's average velocity, so it's the position that you use there, okay? If it's average acceleration, then it's velocity that you use. All right, now we're going to keep using the calculator here, because when on the way up could the projectile, I need to retype that, projectile hit the red baron? Well, where is the red baron? He's at 5,200 feet, and he's up there the entire time. So I'm going to come back to y equals, let's go back to y equals, and let's type in that altitude here. So 5,200, because that's y equals. Now if I go to graph, look, there's the red baron flying along, and I can find these intersections very quickly. So when on the way up? Well, this first part of the graph, that's going to be on the way up, right? So what I'm going to do is I'm going to hit second, calculate, intersection, that's 5. And then the first curve is the blue one. Second curve is the red one. Now, to make a guess, I don't want to be over here, otherwise it's going to find the one that's on the way down. So I'm going to hold left, although you know what's way faster? Is to type in a number. I look at that, I'm going, that looks like it's around the 1 mark, right? So I'm just typing 1, enter, bam, and it jumped over there and found it. It was actually 2.3. I was off a little bit, okay? So when on the way up, could the projectile hit the red baron? That is, the x is the time. That is 2.309 or 2.310. So 2.310 seconds, okay? What about on the way down? Well, on the way down, that's the other side. So second, calculate the intersection. Again, there's the first curve. Yes, that's the second curve. And my guess, I'm not going to take a whole lot of time. I'm just going to guess about 20. And who knows, it's 18.940. So it's pretty close. But again, you just kind of have to get in the area. So instead of holding down the button, that speeds it up a whole bunch, right? 18.940 seconds, okay? What is the projectile's velocity if it hits the red baron on the way up? Well, to get this, we're going to plug this into the second equation here, because that's the velocity. And what are we going to plug in? We're going to plug in the time that it would have hit the red baron. So let's come here. I'm going to leave this, hop out of that. I can do this just real quickly here. Negative 32 times 2.310 seconds plus 340. And we get 266.08. Now something worries me here. You guys see how we don't have 3 decimal places? I didn't use all the possible decimal places. And so what I would like to do is I'm going to go back to trace. And I'm going to find that intersection again. First curve, second curve. That's 2.3099158. Okay. 2.3099158. Let's write that down in parentheses here. 2.3099158. I'll have to investigate. I believe there is a way to use a store function in the calculator for that. But in the meanwhile, what I'll do is I'll go ahead and hop back out of here. And let's go up and let's change this and be more accurate and see if we can't get more decimal places. Okay, so delete that. Again, second insert. lets you type in things right where you want to. 158. That didn't take too long there. And aha, that is more accurate, which means that we need to be careful to keep all of our decimal places. Okay, so this is a lesson. So 266.083. That's meters per second. Oh, nope, sorry, that is feet per second. Sorry, feet per second. Let's follow it. Feet per second. Okay, so that's the velocity. Then on the way down, we want to do the same thing, find the other one. Let's get the more exact number again. So second, calculate intersection, enter, it's close to 19 or so. 18.940, so let's write that down. 18.94084. And what I'm going to do is I'm going to hop back over here, press up, enter. Of course, if you have an older calculator, you can press second enter, and it pulls up previous items. Second enter. If you need, remember that calculator, handy dandy calculator skills video. Might be a good time to go revisit that. Oops, registering my clicks. Those are all the decimal places. So we press enter, and we get negative 266.082. Wait a second. That's the exact same thing, but negative. That is actually going to happen for when things are projectiles, when they're free falling. Okay. And the reason is because of the symmetry. Now, notice you want to be careful. Don't just memorize, oh, it's going to be the same thing but negative. That's not the case for the seconds, right? Time keeps going forward, but the velocity is actually the same as negative. Now, is it important for us to have that negative there? Yes, because it asks for velocity, which includes direction. So it matters whether it's positive or negative, all right? All right, if the projectile misses the red baron, when will it hit the ground? Hey, we found that out a second ago, right? That was right up here. That was our solution to the quadratic equation. So let's write that down. That's 30.478 seconds. Of course, if I forgot that, what I could do, and if I used the guess and check method and didn't use that, I could come back here to trace and do second calculate. And let's calculate the 0. So left bound, am I to the left of my 0? Oh yeah, anywhere on here is to the left. I don't have to get real close. Right bound, I know that 31 is right past it, so I'm going to type in 31. There's another way to make it fast. And of course, guess, I'm pretty close there, so I'm just going to hit enter. And we found there's that same number, 30.477 if you truncate, or 478 if you round. All right, what is its speed just before hitting the ground? Here we have the time. We need to come back and plug this back into the velocity equation. So we're going to do that. So let's do that right here. So I'm going to come back here, and we already have that velocity equation up. Let's just grab it again. Come back here. I press second enter, and let's type in 30 point. I want to be as exact as possible. So in this case, what I'm actually going to do, you know what? I'm going to use the store feature. So let's come up here. Actually clear that. No. Okay, second enter. So now I'm using second enter to cycle back through all the things I typed in. There it is, and I want to store that as, let's store it as A. There we go, alpha or A. And so now if I type in negative 32A, oops, not D, A, plus 340, you can also store it as X if you want to instead. There we go. We calculated. That was us holding all of the possible decimal places. So we have negative 635.295. Of course, you could write down all the decimal places and write them out, but that's a little bit faster in my opinion. And what was the projectile's maximum height? Here we go. Again, we can use the calculator. Let's calculate the maximum. So second trace, maximum. Left bound, I just need to click somewhere that's to the left of this. I know that 1 is to the left of that. I also know on the right side, 20 is to the right of it. And so I can make a guess. Honestly, you don't have to be that close. The calculator will find it for you. Matter of seconds. 10.625. So maximum height is 10.625. That is in seconds. And I'm just noticing that, oh, sorry. Two things. I wrote down seconds because that is 10.625 seconds, but the maximum height is not going to be the X, it's going to be the Y, right? So not 10.625, it's going to be 63 6,300, 6,306.25. So let's come back and write that down instead. And this is one of the reasons that units is very helpful. It can help you catch mistakes like that. 6,306.25. That is feet. And look, I didn't include the units from that last one. That was, what is it, speed just before hitting the ground? That was in feet per second. And then lastly, at t equals 4, is the projectile speeding up or slowing down? Well, for this one, I'm actually going to grab this graph here. Let's grab this and look a little bit closer at it. Here we go. Oh. And let's come back over here and let's just paste this right here. Here we go. Put it here. I keep making these dots. Oh, that bothers me. Dots, go away. Okay, there we go. If you guys can see that. So I'm looking at x equals 4. Oh, I should have probably marked it on there, but let's just count 1, 2, 3, 4. Looks like right about here. Basically, I know that's going to be to the left of the curve, and that's what I really care about right here. Because is it speeding up or slowing down? Well, there's a few ways to talk about this. One way is to recognize the velocity before and the velocity after. Remember, velocity is just the slope of the tangent line because it's the derivative. So if we picture the slope of the tangent line before and after, is it getting steeper or less steep? Well, it's getting less steep, so it's slowing down, right? Another way to think of this is, what is the concavity? Well, it's concave down, which means that the acceleration is negative, but that doesn't mean it's slowing down, right? It only means it's slowing down if the velocity is positive. And is the slope of the tangent line at this point positive? Well, yes, because it's still going up at this point. So here it's going to be speeding up as long as it's on the left side of this curve, and then on the right side, as it's concave down, it's going to be, sorry, did I say speeding up? I meant to say it's going to be slowing down on the left side, and on the right side, it's going to be speeding up in the negative direction. Okay, so you can see these tangent lines are getting steeper and steeper as you get towards the end, okay? All right, so let's write that down. We'll pick one of those, one of those to say. Let's say it is speeding up, because, and we could say any number of things. We could say velocity at 3.9 is greater than the velocity at 4.1. That's not exact. That's not perfect. Another way to say this would be velocity at 4 is greater than 0. So the velocity is positive, but acceleration is negative. And I know that because it is concave down, right? So this would probably be the best way to say that succinctly, though I think this is a more intuitive way to think about it and to grasp and answer whether it's speeding up and slowing down. Unfortunately, they both match. Thank you guys for watching.